Well, hello again, mathletes, and welcome back. Um, so up until now, we've been dealing with our trig functions, sine and cosine particularly, and those are the ones we're going to focus on today. Um, but we've been looking at sine and cosine around the unit circle. And, we keep referring to them as functions, but we haven't actually looked at them as functions. The input for both sine and cosine is an angle, right? It's theta. Well, theta is not actually a measurement on the unit circle as far as the coordinates go. Theta determines where the coordinates go, but it does not. It's what do you call it? It's not really part of the graphing directly. So we don't. There, that's how I want to say it. It's not an axis. That's how I wanted to look at it. Okay, so what we're going to be doing is taking sine and cosine and actually making theta one of our axes so that we can look at this thing as a function. And so let's go ahead and start out here. I'm going to start just by drawing our unit circle, and it's going to be an incomplete one because we only need to look at certain things. Now the graphs of sine and cosine. Let's try this again. I'm getting better at these circles. Um, the graphs of sine and cosine, not the unit circle graph, but the graph of the two functions as functions, actually proceeds this way. Now, remember that for our coordinates, cosine theta and sine theta are the way we go. So that means that the x coordinate is cosine theta and the y coordinate is sine theta. So we're going to actually start this with looking at sine. So I'm going to label this y and this axis theta. And basically the way I like to do this, I like to mark these out by the quadrantal angles, right? Those are the angles that are here on the ones that hit the axes. And so I have points on either the x or the y axes. Those are called quadrantal angles. Um, and if we look at the coordinates here, here x is 1, y is 0. Here x is 0, y is 1. Over here x is -1, y is 0. And down here we have 0, -1. Okay, so those are the four angles that we're going to use. One of them we're going to use twice. We know that this is 0 degrees here. Up here, in fact, let me put that in a different color just so it stands out a little bit. And I'm going to do this in radians. So this is 0 radians here. Up here is pi over 2 radians. Over here is pi radians. Down here is 3 pi over 2 radians. And then if I go all the way back around, I'm back to 2 pi. So that's the one we're going to use twice, is the 0 and at 2 pi. Now, if these are the points that we're going to use to plot this thing, we need to have them on our theta axis. So I'm going to say right here is 2 pi. And then we'll try to split this. It's actually easiest to do this by halves. So I mark the 2 pi first, then I cut it in half and mark pi. Then I cut that in half and mark it pi over 2. And then I come back over here for my 3 pi over 2. Right? So I mark them out that way. It makes it easier. And then looking at this, we notice the maximum value. In fact, I'm going to mark that on here. So y equals sine theta is the function we're looking at. Where was I? Yeah, okay. So when we're looking at the sine function as a function, let's look at the maximum values and the minimum values it takes. So here we're at 0. Excuse me. Here we're at 0. Coming up to here, sine is now 1. That's because it's our y coordinate. And then sine goes back to 0, and then it goes to -1 down at 3 pi over 2, and then it comes back up to 0. So the most extreme values that it takes are 1 and -1. Okay, so we'll mark 1, and we'll mark -1 here. Okay, now, so we just start walking around the circle and mapping these things from the unit circle onto the actual graph. So at 0, right? So when theta is 0, look right here. Sine of theta is my y value. It's 0. So I have the point 0, 0 here to start with. Now, if I go up to pi over 2, if I let my angle, so I'm letting myself rotate this direction as I go. If I come up to here, to pi over 2, my y coordinate is now 1. So that means at pi over 2, I'm at 1. Okay, so that's the first part of the curve. Then we have to see what happens at pi. So we're rotating again this way, and we go all the way down to here, and we see that our y coordinate is 0 again. So this thing comes back down to 0 at pi. And then we need to see what happens at 3 pi over 2. So again, we're going to go ahead and turn one more time. And at 3 pi over 2, my y coordinate is -1. So that puts me down here. And then if I finish turning the circle and come back over here, that's at 2 pi. Remember, those are coterminal angles, so they have the same function value, which means that we're back at 0. Okay, now you notice if I keep turning the angle, if I go past 2 pi, I still get values, but they just basically start doing the same thing over again. Because if I add another pi over 2 and make it 5 pi over 2, I have the same value as pi over 2. So this is the nature of a periodic function. Now, if we want to see what the graph looks like, we're going to connect these dots. Now, these are not straight lines. These are curved lines, right? So they curve like this, and this keeps going because we can have negative values as well. And this one, boy, that's a bad angle. That one curves that way, and then we can come down here. That's still a terrible. And back up to the top, and it keeps going. So if you really wanted to graph this thing, it goes on forever. And as a matter of fact, let me just do this real quick. Let's open a new sketch. There we go. So there's my grid. Let's go ahead and plot a new function. And let's just make the function sine x. Right? So it'll probably ask me if I want to rescale. Yeah, it is. Okay, switch angle. Yeah, let's switch it from degrees to radians, and boom. So you notice it goes on forever, right? If you're actually graphing this thing, what we just graphed goes from, let me switch the colors on that. Goes from here to here. Right, so that was the section we did. We did what was it right inside this box. Right, but you notice that's just one period. This thing does the same thing over and over and over again. Everywhere you look, there's the same thing. You know, it goes up to 1, back down to -1, up to 1, back down to -1. So these things are actually how wave functions are determined. So when engineers are working on things that have to do with the frequency of something, the frequency and the period have a lot to do with each other. In fact, yeah, the frequency is how many periods go by per second, basically, when you're talking about a moving wave. And the period is just the length of that wave. So now, let's see if we can go ahead and do the exact same thing. Oh, you know what? That was the other thing I wanted to talk about. There's one other thing real quick before we switch over and do the same thing with cosine. I want to talk about the domain and the range a little bit. Okay, so the domain of a function is all the values you're allowed to plug into the function. A lot of the time in algebra courses, it's taught, hey, it's all the x values. It's all the input values, and in the cases that you were looking at, the inputs were all x's. they're not always x's. For example, in this case, we're inputting theta. Theta is not an x, but it is an input, which makes it part of the domain. Now, you're allowed to plug in any angle. They could be positive angles, negative angles. They could be greater than 2 pi. They could be less than 2 pi. It doesn't matter what number you pick and whether it's radians or degrees. You can plug it into sine, which means that the domain is all real numbers. And if you wanted to write that as an interval, it looks like that. If you want to use the math symbol for all real numbers, and your homework does not allow for this, but I wish it did, there's a symbol for a double stamped R. Ugh, let me write that again. It looks like this, right? It's kind of like that realtor sign. That's what it always reminds me of. But it's an R with the spine double stamped is what it is, right? So that's another way of saying all real numbers. Now the range is every possible output. It's all the values that a function is allowed to spit out, right? And if we look at sine, there's limits on what it can spit out. I can't spit out a 2, right? Because there isn't a sine of anything that equals 2. So what it means is that sine is restricted. And if we look at this, all of the y values fall between 1 and negative 1. And they include 1 and negative 1. So we would write the interval this way. The range goes from negative 1 to 1. Okay. It turns out the same is true for cosine. You can plug anything into cosine and it never has values bigger than 1 or less than negative 1. So everything is inside that interval from negative 1 to 1. Okay, so what I want to do now, I'm going to leave this unit circle up and let's see. I'm going to see if I can erase this to the point where I can just reuse it. We'll see. I need to get rid of that and that. I can relabel a couple of things. Okay, that goes there. That was pi. That was 2 pi. And we'll just connect that back up. Okay, now, so let's see if we can do the same thing with cosine. I'm going to get these guys off of here too. So it's making that a little messy. All right, so let's start with cosine of 0. Let's just remember cosine is our x value. So now, and I have to hedge this too. This is a technicality and most graphs don't do it. But remember cosine is your x value. So really this vertical axis should be x and the horizontal axis is theta. Right? It's very subtle. Most of the time you see y or f of theta. But technically, because we're building this directly off of the unit circle, and that is an x coordinate, we should use x for our vertical axis. But that's okay. So let's just go ahead and start right here with 0. So if I plug 0 into cosine, and it is the x value, that means at 0, my value is 1. Let me switch colors. Right? Now, if we go ahead and head up this way to the second point at pi over 2, I see that my x value is 0. Excuse me. Okay, so if we jump out to pi now, so I'm just going to keep following the circle around, I see that my x value is now at negative 1, so I'm down here. And then 3 pi over 2, I'm at 0 again, so I came back up. And then at 2 pi, I'm back to the first value, which is at 1. And so we end up with this. Let's see if I can, I gotta move some things so I can get the right angle on this. Right, so it ends up doing this. And coming back around, and it flexes and goes back down again too, just like the other ones do. And as a matter of fact, had you just started it here, the rest of the curve looks a lot like sine, if you look at that. But in any case, This is one period of cosine. After anything, if you step onto either side, you're going to be repeating values again. But yeah, this is the cosine graph. It comes down, it goes through pi, it starts at 0, 1, and it goes down through pi over 2 at the x-axis, bottoms out at pi, and comes back up to 3 pi over 2 into the top. Now, um, just to kind of get an idea here, let's go ahead and look over here. I'm going to make this guy dark. We'll darken that. And yeah, that'll be fine. Let's go ahead and plot one more function. This time, let's do cosine x and see what that looks like. You notice, ah, let's change the color so we can see it better. Let's make it that color and bold it. Okay, so you notice that it's the same shape as sine. Sine is here in purple. Let me make this bigger. Let's get these things off of here. There. Okay, so sine is here in purple. So you can see I go up. This is pi over 2, down to pi, back around over to here. Now, cosine, in fact, I think it'd probably be easier if I just do this. Right? If I look at this spot from here to here, you can see the cosine curve coming through that starts at 1. But you can also see, if you just carve out a different piece of this thing, it's the same shape as sine. Right? Sine starts at 0, but they're just, all they are is the same curve, and they're shifted off by pi over 2. Right? If you measure this distance at any point between the two curves horizontally, that distance is always pi over 2. And you notice as I connect this thing, it's starting to look a lot like a DNA strand. There's a reason for that too. This is actually a helix if you look at it in 3 dimensions. But since we don't have 3 dimensions to play with, I've been trying to find a good prop to show that to you guys. How the unit circle, the spiral, and the sine and cosine curves connect, because they're really all the same 3-dimensional curve that you're looking at from different angles, is really what they are. Okay, so let's go ahead, close that up. So here's what I want you to take from the graphs of sine and cosine. So we'll get that off of there. Let's go ahead and switch back to this. Okay, so sine, if you're going to graph sine, you want to have the key points, which are 0, pi over 2, pi, 3 pi over 2, and 2 pi. Right? Those are your quadrantal angles. Those are the ones that line up with the in between the quadrants. Okay, and I know it's going to be sandwiched between -1 and 1. And then let's see here. Sine starts at 0, goes up to 1, down to pi, down to -1, back to 2 pi. Right? Back to 0 at 2 pi. And so that curve looks like this. One period of this curve does something along those lines. You need to know this basic curve and what these 5 points do. They're actually going to be really important because we're not always going to be keeping it to the unit circle. So as we change things, you're going to need to be able to modify those points. So, but you should know those to start out with. So this is sine theta. If I want to look at cosine theta, same points are important. Right? But this time, we start at 1, go down to pi over 2, down to pi, back up to pi over 3, and then finally top out over here at 2 pi. So you need to know the basic shape of these graphs. Because basically we're going to be modifying these to get a hold of stuff, is what we're going to do. In fact, we'll start modifying them today, but these are our two basic things here. Okay, now, so the question starts to happen here. What happens if I had something like y equals 2 sine theta? Okay, so this number out in front is called the amplitude. And it controls the height, right? How spread out it is. Does it stay at 1, -1, or does it spread out to higher numbers, or does it compress to lower numbers? So in this case, we have it as 2. So our amplitude is 2. Now, if I'm going to graph this thing, I'm going to actually start with a little, let's do this. I'm going to make a little table. Yeah, let's do it this way. And I'm going to start with sine theta. And then we'll look at 2 times sine theta. Okay, so we have 0, pi over 2, pi, 3 pi over 2, and 2 pi, right? Those are our 5 points, and we know it goes 0, 1, 0, -1, 0, right? And we can pick those off from the graph. It's 0, 1, 0, -1, 0. Now, if I have 2 times sine theta, that means I'm taking these values here and I'm multiplying them by 2. So if I multiply 0 by 2, I still get 0. If I multiply the 1 by 2, it turns it into a 2. And then 2 times 0 is 0, 2 times -1 is -2, and 2 times 0 is 0. Okay, so we have all that business now. Now, what if I went ahead and graphed this, and I really didn't leave myself much room. I thought I'd have more room than this. We'll do it this way. What it ends up doing is it changes the range of the sine function. So I'm going to do a tiny graph here. Right, so if I'm looking at sine here, I still start at 0, 0, right? I can see that, 0, 0. And then I go up to 2 at pi over 2, down to 0, and then down to -2 at 3 pi over 2. So what it does is it stretches it out. Right? And that's how you piece it together. But if you know the amplitude is 2, the easiest thing to do is just stretch the thing till it reaches 2. Right? Just those things that used to be at 1s, make them at 2s, and then you're fine. Right? It takes care of everything. In fact, if we look at it here, right, let's see what happens. I'm going to plot one more function. Let's plot another new function. This time we'll make it 2 sine, oh, it doesn't like that. I have to do times. 2 times sine x. Let's see what it does. And you notice, here's sine x, right? That's this guy. 2 times sine x just basically stretched the humps out till they reach 2, right? That's pretty much all it did. So whatever number is in front, right, that tells you the amplitude. So if that number in front was a 2, as it was in this case, right, as it was in the case here, then what it does is it changes my range to -2 to 2. Okay, so let's go ahead and clear this off again. Right, so now if I end up looking at something like this, let's say I'm given f of theta is equal to 1/4 cosine theta. right? So automatically amplitude is 1/4, right? You already know that. That means the highest it goes is 1/4, the lowest it goes is negative 1/4. So if I'm going to graph this, I need all my same points. Right? And if 1 is up here, then we'll just say that's 1/4. That means I only go this high. So if this is cosine, that means I start here at 1/4, go down to here, I go down to negative 1/4, up again, and so we have this really shallow curve this time. Right? So it just kind of flattens it out. And it's true for sine or cosine. Whatever it happens to be, all the things that used to be ones turn into whatever your amplitude is. Right? Okay. So let's look at one more here. Let's look at g of theta is negative. Let's make it -3 sine theta. Okay, so now we have a negative number here. So we still, even though it's negative, we still say the amplitude is 3. Right? And it's a sine function. I know I'm going to be, if the -3 wasn't there, I'd be sandwiched between 1 and -1. Now I'm sandwiched between 3 and -3 still. But what does that negative do? You know, if you think about all your other functions, if you throw a negative in front of them, it flips it upside down, right? If I have x squared, that goes up this way. If I do negative x squared, it goes down this way. So it flips things over is what it does. So let's see. And you can actually just work it out directly also. Okay, so you actually could work it out this way. Just take each value of sine and multiply it by -3. So here, normally I'd start out, I'd get sine of 0 is 0. 0 times -3 is still 0. Here, sine of pi over 2 is 1. 1 times -3 is -3. And so you notice it's flipping things upside down. Now, sine of 0, or sine of pi is 0, and -3 times 0 is still 0. And then 3 pi over 2, sine of 3 pi over 2 is -1, but this -3 says we're multiplying the -1 times the -3, which makes it a +3, and then back down to pi over 2. And so the negatives flip them upside down. Let's see if I can draw this. It's a weird angle. Usually I can take my paper and turn it all different directions. It doesn't work like that when I'm writing on a screen. Okay, right, so basically it did stretch it out still, right? Its range is still -3 to 3, right? It hasn't changed anything. And by the way, nothing we're doing right now will change the domain. It's always all real numbers for both of these. But yeah, so you have to be able to deal with the changing amplitude. That's the main thing. So there's two things I really want you to get out of this lecture. The one is to be able to just do the basic graphs of f of theta equals sine theta and f of theta equals cosine theta. Right? You should know the basic graphs. What happens with those two functions at 0, pi over 2, pi, 3 pi over 2, and 2 pi, all your quadrantal angles. Okay, so you should be able to graph both of those. You should also be able to deal with what happens with the amplitude, right? So if the amplitude changes, how does that change your graph? We actually have a whole bunch of things that are going to be changing our graph. So we can change the shape of this wave as we go through. A fully generalized, sine or cosine function, um, they look like this. A sine bx plus c, not plus c, plus d, plus d. A, B, C, and D all change the function in a particular way. And if you understand all four of those, you will be able to graph any sine function. Okay, right now we're only dealing with A. We're going to be looking at the rest of these. B and C we handle together, and it kind of makes sense. They even look like they're put together. And the same is true for cosine. You have A cosine bx plus c, and then a plus d at the end, right? So all of these things, and they do the same thing to both functions. It's just they happen to have different starting points, so they look a little bit different, but they pretty much do the same things. What we found out right now, and remember, it doesn't matter the sign, the amplitude is always positive. So the amplitude is the absolute value of A, right? Incidentally, when you talk about AM radio, the A in AM stands for amplitude. AM means amplitude modulation, which means that all of the information in the wave is carried by changing the amplitude, right? So the amplitude's changing, and that's what tells the radio what sound to make. It's actually why with an AM radio, when you drive under a bridge or something like that, the volume goes down. You notice it doesn't really do that with FM. And that's because FM stands for frequency modulation, which means that it's affecting the period, right? So they change the period a little bit, and that's where the information is stored. And so, if your radio can still see the changes in the period, even with a lower amplitude, it will still produce a sound, which is why you generally hear FM radios pretty clearly as you go underneath something. What you get instead on FM radios is static, whereas AM radios, they drop in volume. So it's kind of interesting how these things are used, but they really are used regularly. Um, these periodic functions get used to model all kinds of things that repeat themselves. The temperatures throughout the year, um, the tides, right? Tides go up and down, and they do it in a predictable manner. So that means it's a wave function. And so all wave functions can be represented in terms of sines and cosines. All of them can. In fact, if you happen to be one of those people who is going far enough in math, you will see that all functions can be rewritten in terms of sines and cosines. It doesn't matter what they are. You could take x squared, a parabola. You can write down a series of sines and cosines that when you add them up, they turn into x squared. It's pretty crazy stuff. So anyways, that's what I wanted you to get out of today. And so until next time, keep your pencils and your wits sharp.